Boy, are we getting to learn a lot this year. So we are starting chapter 6, and we're going to be talking about circles. So circles, in order for us to get started on circles, we really need to go through some vocabulary. So Coach Fred doesn't love to go through vocabulary, but so what I did is I gave you your note sheets. I gave you the words, so instead of you writing the definitions, I've given you the definitions. We'll talk about them, and we're going to draw them. A prettier way to look at definitions, okay? So a circle is a set of all points in a plane, which means on a flat surface, that are equidistant from a given point called the center. Okay, so you've got that circle there. So here's the center. We always put a dot, and let's call this circle R. The definition says that from that point, there's this set of points that are equally distant all the way around from that point, okay? And that's what we call a circle. Now, there are an infinite number of points on a circle. I want you to make sure you put that dot in there. And we know that that leads us into our next definition, the radius. That distance from the center, so in the little description box, I want you to put the radius is from the center, so a segment from center to the circle. The definition says a segment whose end points are the center and any point on the circle. So a radius can be drawn like that. It could be drawn like that. It can be drawn like that. It can be drawn like that. The big thing for us to know is that all radii, R-A-D-I-I, all of them are congruent. No matter where I draw them, they are congruent, and you're going to have to be looking for radiuses in very weird places that don't look like radiuses, but they are. But it has to come from that center. Okay. There's other pieces or things that happen in circles. There's a segment whose endpoints are on the circle. That's called a chord of the circle. So a chord would look something like this. In the description, I want you to make sure you put a segment, and it must end on the circle. Okay, so a radius is actually not a chord because it starts at the center and goes to the circle. All right, a diameter. A diameter is actually a very special chord. It is a chord that goes through the center. Okay, so something like that. It's half a radius. That's what we're going to put in the description box. Half a radius. It creates two semicircles. And a diameter can be drawn many different ways as well, as long as it goes through the center. Like that. My line didn't want to go. Or like that. Those are all diameters. All right, a secant. A secant is a line that intersects a circle in 2 points. So that, with arrows at the end, is a secant line. Now, you may say, well, it's also a chord. This part of it is a chord, okay? If it extends beyond, then it is a line. So then it would be a secant line. All right, the most important line that relates to a circle. A line in the plane of a circle that intersects the circle in exactly 1 point. Something like this. It hits the circle in exactly 1 point right there. That's called a tangent line. Okay? A tangent line doesn't just have to, something can be tangent to a circle, to a curve, to an ellipse, to a hyperbola. It's a line that touches something in one place, exactly one place. That one place is called the point of tangency. Which is our next definition. The point of tangency, the point where a tangent intersects a line. So let's draw another different point of tangent line. There we go, like that. That right there is the point of tangency. All right, so we've got to be able to identify what parts there are. So here's an example. Tell whether the line or segment is best described as a chord, a secant, a tangent, a diameter, or a radius. All right, so my symbols are kind of off here, but AD, okay, so A here to D here. Well, it is a chord. because its endpoints are on the circle, but it also goes through the center, so it is more specifically a diameter. Okay? All right, CD. CD starts at the center, goes to the circle, so then that would be a radius. Take a second and look at that, okay? Okay, EG. So E to G is off the circle. Now we're going to put the symbol like this above it, line symbol on EG. And EG is hitting the circle in exactly one place, so it would be a tangent. Tangent segment, a tangent line, we could actually use both, okay? HB. HB is a segment. It is on the circle. Its endpoints are on the circle. That's considered a chord. FB. Now you may notice that the nothing is drawn there, but I am allowed to draw lines and circles. If I connect F and B, the endpoints are on the circle, so it would be a chord. FE, you might be saying, is a segment. That segment actually touches the circle in one point, so it is a tangent segment. Segments and lines can both be tangent to a circle, okay? All right, so you are going to have to know your terminology. May be helpful for you to make a Quizlet. Now we're going to put it to use. So our first theorem that we're going to be talking about relates to a radius to a tangent. I call it the radius to tangent theorem. All right, so we're going to take a circle. Oops, mine's kind of big there, sorry. And I'm going to draw a tangent to it. Now, if I take a radius and I draw a radius directly to the point of tangency, it creates a 90-degree angle. They are perpendicular to each other. So the theorem actually says if a radius is drawn to a tangent, it is perpendicular at the point of tangency. That's important. So anytime you need help, you can actually go from the circle right to the point of tangency, and that creates a right angle. Now, what you might see is that we might be able to use that because if I connect any point on the point of tangency like that, I have now created a right triangle. Remember, there's those right triangles, okay? All right, the next theorem, the clown hat theorem is what I like to call it, the clown hat theorem. If I take a point and a circle, and I draw from that point 2 points of tangency, or 2 tangents from that same point, their distances would be equal to each other. So these segments from that point to the point of tangency would be congruent. So tangents to a circle from the same point are congruent. Okay? All right, so let's apply both those theorems. Example 2, it says verify a tangent to a circle. Verifying a tangent to a circle. We're going to actually be using the Pythagorean Theorem converse. So here you might see that this line right here is a tangent, and this is a radius. So I want to verify that it is actually a tangent to the circle. So if it were a tangent, then that means those would have to be perpendicular, which would mean that this whole triangle would need to be a right triangle. In order for me to tell if it's a right triangle, then a squared plus b squared has to equal c squared. All right, well, one thing you might notice is this is a radius, and this is a radius. So this length is 6. This length right here is 4. So I have to add them together to get the whole side, which is 10. So I do 6 squared plus 8 squared equals 10 squared. Does 36 plus 64 actually equal 100? Yes, it does. So that is a right angle. It is a right triangle, so that is a tangent line. All right, now some of you might have said, Coach Fred, I didn't need to do that. It's a 6, 8, 10 Pythagorean triple, and you're absolutely right. If you saw that, then it would be okay. You'd be able to do that. All right, let's look at the next one. I want to prove that this is a tangent line, okay? That it is actually tangent to the circle, which means I need to prove that this triangle is a right triangle. All right, so 9 squared plus 12 squared, does it equal 15 squared? 81 plus 144, does that equal 225? And yes, it does. And then you might say, Coach Fred, that's a 3, 4, 5 triangle. So yes, it is a Pythagorean triple, so it also works. So that means it is a right triangle, and that is a tangent line because they are perpendicular to each other. All right, the clown hat theorem. The clown hat theorem, you can see things totally in many different ways. Oh wait, where did my clown hats go? Okay, so wait, let me draw it again. All right, I'm going to take a circle. Sorry about that, guys. And you can see in the example that from point R, you had a tangent like that and a tangent like that, and that's the center C. And that is from a point of tangency, from a point to the circle, those segments would be congruent. So then 2x plus 3 equals 25. So 2x plus 3 is congruent to 25, so I can set up an equation. I would subtract 3 from both, and I'm going to get 2x equals 22, and therefore x equals 11. All right, the other triangle. I look, there's a point and a circle, and I have 2 tangents drawn to the circle. That makes it the clown hat theorem, so these are equal. So x plus 12 would have to be equal to 4x plus 9. So 4x plus 9 equals x plus 12. And so 3x equals 3 and x equals 1. All right, one other thing about these two properties, I'm actually going to put them together. So at the bottom of the page, what I'd like you to do is I'd like you just to draw a circle. And I'd like you to draw 2 tangents to the circle from a point. I'm going to switch colors here. And I'm going to draw those 2 tangents, one here and one here. Now I'd like you to label the center of the circle and label those pointed tangencies like that with dots. And now from the center, I want us to draw a radius to both the points of tangency. That creates a 90-degree angle on both of them. Now I'm hoping that you see that we've created a quadrilateral. And I'm going to call this angle A and this angle B, or point B, so angle B. If these two are 90 degrees, what does that tell me about angle A plus angle B, the measure of angle A plus the measure of angle B? Well, I hope you're saying that a quadrilateral, the 4 angles of a quadrilateral have to equal 360. And if I already have 2 that are 90 degrees, that's 180 degrees. That tells me that A plus B together have to equal 180 degrees. So when we use both of these theorems together, these 2 angles are supplementary. So this angle plus this angle will always equal 180 degrees. It's just a nice cool thing that comes out of the clown hat theorem and the radius to tangent theorem that we may have to use in the future. All right, so what I would like you to do is I'd like you to try and do page 4 of your packet and bring it to class tomorrow for us to check. All right, guys, have a great night.